Hello, everyone. This is going to be the last lecture of this course. And in this lecture, we're going to talk about the remaining issues of support vector machines. So in the last lecture, we talked about the support vector machines, and we talked about the binary linearly separable or strictly separable case. And our picture intuition is to maximize the margin between your data samples and your decision boundary. In this case, you can formulate the idea as a minimize half of the norm of W squared subject to, for every data sample Tm, W transpose Xm plus B should be greater than or equal to 1 for NAM from 1 up to M. Okay, and we mentioned that in this case, it must be linearly separable or strictly linearly separable. Otherwise, you cannot solve the dual problem. Or if you solve the dual problem, probably it does not converge or it does not give you the correct result. But in real applications, oftentimes our data is not linearly separable, okay? Just like here are some samples and here are some negative samples. In this case, it's not linearly separable, you see? It seems like this, okay? And in the Gaussian discriminant analysis, maybe we have a cat, the size and weight of cats and dogs, if they have the same variance or the covariance matrix, the decision boundary is linear, right? Suppose they have the same covariance matrix. But still, in this case, for an animal here, you can't tell which animal it is for sure, right? It can be either a dog or a cat, but if it's here, it's more likely to be a cat. If it's even closer to the center of the cat, it's even more likely to be a cat, but you cannot tell absolutely for sure, right? So in practice, we still want to have a linear classifier or linear hypothesis class to solve non-linearly separate problem because of first, maybe the Bayes classifier is linear. So I know that a linear classifier is the best. Or even if the Bayes classifier is not linear, sometimes you still want to use the linear classifier as the hypothesis class to achieve the bias variance trade-off, right? If your model is too powerful, then it's less generalizable. And sometimes you want to sacrifice some of the training performance, but your model will become more generalizable. So in these cases, the linear classifier is still preferred, even if your data training samples are not strictly separable, okay? But we cannot use this formulation to solve the problem. It gives you, the feasible set is empty, okay? There's no such W and B that satisfies all the constraints. So the idea is we are going to introduce the soft margin SVM. Okay. So here you can think of this, the hard margin SVM or hard SVM, where it says your data samples must be strictly off the margin or on the margin, okay? It cannot intrude the margin. If it intrudes the margin, then you must adjust your margin to make it off the margin and also on the correct side. But sometimes this is not doable. So the soft margin idea is maybe a few samples can intrude the margin. And if you intrude the margin, I will give you a soft penalty, okay? So the idea is, maybe I have a few samples here, okay, but I have some outliers like this, or some noise of the label, it's also possible, right? But generally speaking, this half space is red and that half space is blue, okay? So this time, it's fine if you intrude the margin, but I have a penalty for you. The penalty is proportional to how much intrude the margin. Suppose this is my margin, okay, for the blue samples. And this is the margin for maybe, okay, for red samples. So the idea is, if these samples are located in the correct side of the margin, then you are fine. Okay, you are good. If you are on the margin, it's also fine. But if you intrude the margin or you go to the opposite side of the decision boundary, you're going to have a penalty. And the penalty is proportional to how much you intrude the margin, okay? So for these things, so suppose this is my penalty axis, okay? This is my penalty. For these samples, you are good. But if you have a sample here, then you intrude the margin by that much, so you will have a penalty of this, okay? And if you intrude the margin by that much, you will have a penalty of this, okay? And if you have samples like this, then you have penalty like this, okay? So these segments, the length here is how much you intrude the margin, is also how much your penalty is. So the penalty is linear in terms of how much you intrude the margin, okay? So this is my penalty. Likewise, for the red samples, I also have a penalty which is proportional to how much you intrude the margin. Okay, so all the samples here are good, you are good. And the samples on the margin, okay, you are also good. But as long as you intrude the margin, and you have a penalty proportional to how much you intrude the margin, okay? And you sum them together, okay? So this is the basic idea of the soft margin. And this time, you know, the greater than or equal to 1, it's not a hard constraint. Some samples can intrude the margin for a small extent, but you will be penalized by how much you intrude the margin. So we're going to revise the formulation as saying minimize WB half of W squared subject to W transpose X M plus B greater than or equal to 1, okay? But I allow you into the margin by psi for every data sample, okay? So suppose the sample into the margin by 0.5, it's here, it's halfway from the margin to the decision boundary. Then this term, you know, suppose we consider the positive samples, then T is positive 1. Then this term is 0.5, okay? It's halfway between the margin and the decision boundary. Suppose psi is 1, then it's precisely on the margin. If psi is 2, then it's greater than or equal to -1. It means that you are on the margin of the wrong category, but it doesn't matter. You still have a penalty of 2, okay? But if you are in the correct side, for example, if this term gives you 2, then the psi is still 0. So psi must be greater than or equal to 0. So if you are here, you don't have reward, you don't have extra bonus. But if you intrude the margin, you have a penalty. And the objective is to minimize not only W, but also how much you intrude the margin. And C is the hyperparameter controlling the strength of the penalty of how much you intrude the margin and how much you would minimize the norm of W. So if C goes to infinity, then it becomes the model, the soft SVM converges to a hard SVM, okay? As long as you intrude the margin by a very small number, you will be heavily penalized, okay? If C is small, then more samples can intrude the margin. And if C is 0, or converges to 0, then you don't have this penalty, and the problem becomes this number must greater than or equal to 1 minus something, and psi is also your optimization variable, okay? Then of course it will be greater than 1 minus some numbers. For example, I can say my psi is 1 billion, okay? Of course it will be greater than or equal to some number. Then it's not very well defined. Then my W is 0. It's not meaningful, okay? And C is a hyperparameter. It can be determined by hyperparameter tuning, okay? So we're going to compare the soft, how to solve this problem is the homework. But we're going to compare the soft SVM and the good old logistic regression. Okay, the loss, in particular, the loss of SVM and the L2 penalized. Okay. So suppose this is my Z, which is W transpose X plus D, okay, for a particular data sample. And in here, it's my loss or my error, okay, or error. The loss is less the L2 penalty, okay. So we ignore the L2 penalty. L2 penalty can be applied in the logistic regression, and it's equivalent to the minimization of W here, okay? So let's ignore the L2 penalty. And also, without loss of generality, we assume we consider a positive sample, okay? For a negative sample, it's analogous. But for the SVM, the negative sample target is -1. For logistic regression, it's 0, but it doesn't matter because it's just the name of the negative sample. They have the same nature. So what is my error? So my error is if you are greater than or equal to 0, C is W transpose X plus B. If it's greater than or equal to 0, you are good. You have no error. So I can use another color, maybe gray. Okay. If it's less than or equal to 0, then you will predict the negative sample, but you make an error because we assume we consider a positive sample. Then your error is this. This is your error, okay? And how is the 0 point determined? It's not a big problem. I mean, you can think of here you exclude the 0, but it's generally not an issue. What is the loss for the support vector machine? Okay, the support vector machine is a linear loss. How much you into the margin, which means how much this term W transpose X plus B is less than or equal to 1. Okay, so suppose this point is 1, then it's a linear term. Okay, so it's just similar to here, you know, or here, but you need to flip it. Okay. But if your W transpose X plus B is greater than or equal to 1, then you are good. You have no penalty, no loss, okay? So this is my loss of SVM. Exclude the L2 penalty, okay? Then what is the loss for the logistic regression? We use the cross entropy loss, which is the negative log likelihood. So the log of likelihood is the probability, but the probability is the sigmoid function is the exponential of minus W transpose X plus B. Okay, but this is just C. Okay, so let's say it's so I can say this is log of 1 exponential over minus z, right? Because you can say this is -1 and this minus cancels with that, okay? Then we know if z goes to infinity, then the cross entropy loss, if z is infinity, then minus infinity is minus infinity. Exponential of minus infinity is almost 0, then it's almost log 1, which is 0. Okay. If z is 0, then its exponential of 0 is 1, so it's log 2. Okay, log 2 is probably some point here, so I can use another color here. Okay, if it's large, then it converges to 0, but it's 0, then CE is log of 2. If z goes to minus infinity, then you know, this is exponential of minus infinity is infinity, so it's going to be infinity. But we care about how fast it increases, right? But then you consider like, oh, this is exponential of infinity. It almost dominates 1. So the 1 is negligible. Then you have the log of exponential of minus z. So the ratio how it increases is just minus z. It's just 1. Okay, the slope of your increase is just 1. It's just a linear line. Okay, so you have a asymptotic linear increase, and your loss is something like this. Okay, so this blue curve is the cross entropy loss. Right. So this is just a rough thinking of why it increases linearly. But otherwise, you can consider the cross entropy loss divided by z, okay, as z goes to minus infinity, and you can use the L'Hopital rule to compute the ratio. But roughly speaking, it's just linear and it's obvious. Okay. And this plot just tells us that linear SVM is very similar to logistic regression. In a real application, if you try linear SVM and if you try logistic regression, it almost always gives you very close results because their loss is almost the same, right? You see they are almost the same, except that the SVM, the loss is sparse. It only has a loss if your z is less than 1, okay? But cross-entropy loss always has a loss. Its loss is strictly non-negative. But if you predict it correctly, then it's very close to 0. Okay. And in both cases, you can think of it as a differentiable approximation of this step function. Okay. And by the way, you can definitely also use the mean square error for linear classification. And in this case, your loss is the green quadratic curve, okay? And it doesn't give you good results for obvious reasons, right? You predict it very correctly, but you have a large loss, okay? So this is not fancy. Okay, so this time we are clear that if you want to have a linear classifier, but your data is not linearly separable, then you'd rather use a soft margin SVM. And this is what we do in practice. So in practice, we never use the hard margin SVM. That is only for introductory purpose, okay? If I introduce that model that is simpler and it's intuitive, then we can develop on that and introduce the soft margin SVM, which is almost always used in practice. The next thing is, how about multi-class classification? We mentioned that the SVM is intrinsically a binary classifier. It's very elegant, but in terms of multi-class classification, it's not an elegant model, but you can still do that and it gives you good results, but it's ugly, okay? It's not a very elegant model. So there are a few approaches to do that. The first approach is 1 versus 1. So let's assume the target is from C1 up to CK, okay? You have K categories for capital K. And it's mutually exclusive. You can only be one of the category and you must be one, okay? So the 1 versus 1 idea is I build K times K minus 1, okay, half of them, classifiers, okay? So I choose all the pairs of 2 classifiers. So this is K choose 2, right? Classifiers, and I will do a voting, okay? But such approach is not very elegant in several reasons. First, the complexity is quadratic, okay? So if you have 3 categories, you need to build 3 classifiers. If you have 4 categories, you need to build 6 classifiers. If you have 20 categories, then you probably need to build hundreds of classifiers. So the complexity is high. And also the prediction is ambiguous. Okay. Suppose we have 3 categories and we're going to do a pairwise comparison. Okay, and suppose these are my results. So this is C3 compared with C2. Okay, let's say this is C3 compared with C2. And this is C2 compared with maybe C1. And this is C3 compared with maybe C1. Okay, it's pairwise comparison. Now we observe that, you know, apparently this part is C3, right? But what is this part? This part says C3 says, okay, compared with C1, C3 says good, C1 says no. And for C2, you know, compared with C1, C2 says good, C1 says no. But from C2 with C3, C3 says good, C2 says no. So you have 2 votes for C3, but 1 vote for C2 and no vote from C1. So this is C3, right? So this part is C3. And likewise, this part is C2. But where is here? You have 2 votes for C2 and 1 vote for C1, but no votes for C3. So this is C2. Okay, C2 is this part. And this part is, you know, you say it's C1, it's fine. But what is this part? So you have 2 votes for C1, but 0 vote for C3, right? And 1 vote, 0 vote for C2. Am I right? So C3 says good. Good. Oh, you have 1 vote for C3, 2 votes for C1, and 0 votes for C2. Okay, so you say this is C2. But what if here? Okay, if you have a data point here, then you have 1 vote from C1, C2, C3. Then you cannot easily determine what is the category. Okay, so the classification is ambiguous. Okay, so that's why 1 versus 1 is not widely applied. It's not a good approach. This is my attempt 1. Another attempt is one versus two. Oh, sorry, 1 versus all. Okay. So in this case, I would like to build still K classifiers for K categories, okay? And it will determine whether this sample may be classified as category K, okay? So maybe category 1 says, okay, you are good. Category 2 says, okay, you are also good. But now I will choose the prediction as the argmax over the category such that W transpose X plus B for the K, okay, for the little k, which has the largest margin. If you have a larger margin, then you classify the sample as that category. Okay. So obviously, 1 versus all is better than 1 versus 1. Its complexity, the complexity is linear to the number of categories, and also it's unambiguous. If you have argomats, they have the same numerical value, it's unlikely. And the third approach is more structured approach. Okay, so suppose the category for some data sample is I, okay, or CI. Then my training, I'm not only training one binary classifier at a time, but I consider all the labels during training. I would require my WI transpose X plus BI is greater than or equal to WJ X plus BJ plus a margin, okay, required. For all J is not I, okay. So in this case, during the training, you have already considered all the categories, all the possible categories. You have already compared the target category with other candidates, okay? So this is more structured way of doing SVM, but this raises some complexity in training or in optimization, okay? And in practice, I guess this is the most widely applied approach for multicast classification with SVM. Our last topic for this lecture and also this course is kernels. So the kernel is used to do nonlinear classification with support vector machines. And the observation is that in support vector machines, the training and the inference only care about the inner product of my data. So the training is the dual problem of support vector machine is summation over all kinds of n and also xn transpose xn, okay? Here, x are the vectors and all other things are scalars. Subject to all alpha is greater than or equal to 0, and the summation over m, alpha m, tm is 0. Okay? So this is the training, and the inference is the decision boundary is W transpose X plus B, and so B is kind of a constant factor, right? But W is summation over M, alpha M, Tm, Xm, right? So this is the decision boundary. And if you put W into this equation, then you will have summation over M equals M, alpha M, Tm, Xm, transpose, because you have a transpose here, X plus B, okay, it's for some B. And again, it only cares about the inner product of your data. Okay, so the idea is if I can use the inner product of some features. Let's transform my data samples by phi. Okay, phi now becomes the features of my data sample. One example is like x1 and x2 and x1 square and okay, x1 and square x2n squared and x1 and x2n. Now it becomes quadratic of x, right? Then I also have the phi of xm transpose, okay? And the SVM, this is my SVM training, only curious about data by its inner product, right? During both training and inference. When the SVM queries the data about the inner product, instead of saying that it's x transpose x, I say this transpose something of m, okay? Okay, phi xn and phi xm. Then the SVM has no idea whether data lives in the x space or live in the phi space. Now you can transform your data into a different space by specifying the inner product. Okay, so this is the main idea. So before presenting the common inner products, I would like to talk a little bit about the inner product in general. So what is the inner product? Okay, so inner product is defined on the vector space. So what is a vector space? So in a finite dimensional vector space, a vector is maybe d numbers, then it's d-dimensional. So it's d1 up to vd, okay? Then it's a d-dimensional, suppose every number is real, then it's d-dimensional real space. But the vector can be generalized to some abstract vectors, okay? So you can think of some abstract vector space. And as long as you satisfy the following axioms, then it's kind of a vector space. So in vector space, we have two operations. One is the vector addition, and the other is the scalar vector multiplication, okay? So for any uv in my vector space, u plus v is also in my vector space, okay? So here uv are vectors. Scalar multiplication says for any number a in my number system. So a vector depends on the field, okay? So you still need a field. Field is a number system. You can think of it as a real field or a complex field or rational field. You have plus, minus, multiplication, division, okay, except zero, then it's a field. A times u is also in the vector space. Here u is a vector, a is a scalar. And you also have to satisfy some properties for these operations, okay? I don't know if I can memorize all the properties well, but let's try it. For example, u plus v is v plus u for any uv, and u plus v plus w is u plus v plus w, but you have different associations. And also you have the zero element, okay, the identity for addition, okay, plus u equals u, okay, for any u. And also you have the identity for scalar multiplication. So exists 1 times u is just u, okay? This one is just the scalar one, okay? It's in your field. It can be a real number or a complex number as you define the field, but the one is just the one you know, okay? Just one. So it's just a scalar one, but u is a vector, okay? Here the 0 is a vector. And also like a times u plus v is au plus av for any a in the field, and the u and v are vectors. Okay. So this is the vector space. For anything satisfy these things, it's a vector. Example. D-dimensional real numbers. A real vector is a vector space, of course, right? So this example just says the vector we know is just a type of vector, okay? Another example is, this is a little bit tricky. Define a function f from maybe 0 to 1, okay, to a real number. Okay. So I have a function from 0 to 1, and it turns out that it's also a vector space. It's also a vector space. Right? So I can define, so I need a vector addition and scalar multiplication. So I need to define f plus g, it's a vector addition. So this function, when you apply x, I define it to be f of x plus g of x, okay? And I also need a scalar multiplication. So for NAA in my scalar, okay, let's talk about a real field. Don't worry about complex numbers. It's just a real field. Then a of f x, I define it to be a of f of x, okay? Then it's very easy to verify that it satisfies all these constraints, right? F plus g is g plus f, because f of x plus g of x is just g of x plus f of x. So this is a vector, but when you write out the function vector of x, then it becomes a scalar, okay? And similar, you can verify this. And the 0 function is f of x is always 0. Identity scalar is just 1, the one that you know. And of course, everything holds. So this is also a vector, okay? It's a vector space. So this shows that by following these definitions, vector is not necessarily a finite d-dimensional vector space. It can be some abstract vector space. You can define some mapping as a vector as long as they satisfy these things, or functions or matrices is also a vector space. Inner product. Inner product is defined on a vector space, and you take in two vectors and I give you a number. So inner product is a V by V to the field, okay? You take in two vectors and I give you a number. And this function, so this is a function, okay? This is a field. So this is a field, and this is a function. This function cannot be any function that satisfies this. It has to satisfy some properties. So let's see if I memorize all the properties well. For NAU, the inner product of UU is greater than or equal to 0. Okay. So it's actually, if you consider a complex field, then the inner product may be a complex number. But if you have the inner product of a vector with itself, then it has to be a real number and it has to be greater than or equal to 0. And UV is 0 if and only if, UU is 0 if and only if U is 0, okay? U is the 0 vector. So it basically tells you that inner product can define a norm of a vector, the length of a vector, okay? The norm can be induced from inner product as this. Okay, so this is one property. The other property is U plus U, U plus V, W is the same as U W plus VW. Okay, it's basically linear. And with some other properties, you can also verify that UV plus W is the same as UV plus UW, okay? But this is not required in the axioms because this can be derived from other axioms. And also, scalar multiplication, I guess, A times U with W is A, U, and W. And also UV is the VU, except that you should take the complex conjugate, okay? And by these two properties, you can define for the second slot, you will have, suppose you have U, why do I need W? I can say this is V. Then suppose I have UAV is complex conjugate of AVU, which is the AVU, which is the AVU. So this gives me UAV is A complex conjugate UV. So when you take the second term out, you should take the complex conjugate. But if my field is real numbers, then it's just A itself, okay? So you just ignore the complex conjugate. Example. For a d-dimensional vector, V is, for example, V1 up to VD. Let's talk about the real number, okay? Then U transpose V is an inner product. Okay. So you can verify all the things here. And another example is, let's consider a function space, and let's even simplify things. Let's say the polynomial to the most m degree, okay, is a vector space, right? You can just verify very similar to this. And I can say for NA, F, and G, the integral from 0 to 1, let's say f of x, g complex conjugate gx is also an inner product. Inner product. Okay, so you can verify all the constraints. So this is not constraint. It's the definition of inner product induced norm, but you can verify all the other things. Let's just talk about, for example, this, okay? So I say integral over f1 plus f2 g complex conjugate dx is, I don't even have to say dx, just for simplicity. It's just f1 g complex conjugate plus f2 g complex conjugate, then it's the f1 g plus f2 g, okay? So it's almost obvious that it satisfies all the constraints here. So it's a inner product. Okay. So with these abstract notations of vectors and inner product, it gives us the more generalized tool that we are working with the more generalized space. And some of my features may not be a finite dimensional space, okay? The features can be maybe a function of course, you have more values in the function than a finite dimensional space. Okay. So example. If I define xn, the inner product between two data samples as xn transpose xn, okay, to the power of d, then it essentially defines a polynomial feature. Okay, so let's simplify notations. Let's call xn as x and xm as z. Okay, otherwise there are too many superscripts and it's very confusing. So let's say the inner product of x and z, where x and z are in my vector space, okay, is 1 plus x transpose z to the power of d. But let's just say the power is 2. Okay, let's see what happens. And let's also assume that x and z is two-dimensional features, okay? Just for simplicity, two-dimensional real vectors. So it's actually saying x and z, the inner product, is 1 plus, what is this? This is x1, x2 transpose z1, z2. And this is essentially x1, z1 plus x2, z2, okay, to the power of 2. So it's essentially 1 plus x1 squared, z1 squared plus x2 squared, z2 squared plus 2 of x1, z1, sorry, plus 2 of x2, z2, plus 2 of x1, x2, z1, z2, right? Then this can be written as, okay, so I would like to decompose each term into x only or y only. So I would like to say this is the vector transpose vector, and then you have element multiplication, and then you take the summation. So I want to group each of the additive term into x or z only. Okay, so I say this is 1, and the second term is x1 squared. This is z1 squared, and the third term is x2 squared, z2 squared. The fourth term is square root of 2x1, square root of 2 x2 z1, right? And the next term is square root of x2, square root of z2, and the square root of x1, x2, and square root of z1, z2, okay? So if I specify my inner product like this, by the way, the inner product is the kernel of x and z. Then I can write this, okay? Then I'm implicitly transforming my features of x, okay, into this x1, x2 square root of x1, square root of x2, square root of 2 of x1, x2, okay? So something like this. So I'm implicitly transforming my data features in the x1, x2 space into 1, x1 squared, x2 squared, then some factor x1, some factor x2, some factor x1, x2. Now you include quadratic features, right? I didn't do that explicitly, but by applying the kernel, I say my inner product of x and z is this. Then it's equivalent to transforming the features into a higher dimensional space. Then you do a linear inner product in that space. And the SVM has no idea whether your data is living in the X space or in the phi X space. And it can perform a linear classification in this space, but it turns out to be nonlinear in the X space. Okay. And the complexity of computing the kernel is actually better than the complexity you transform it to the higher dimensional space and you compute the inner product. Because if you do it by the kernel, X is d-dimensional and Z is also d-dimensional, the complexity is OD. Okay. But in here, the complexity is OD squared. Okay. It's actually more efficient than you transform the features explicitly and then you compute the inner product. You don't have to do that. You just compute the inner product from some kernel trick, and it's actually equivalent to map it to the high dimensional space. Okay. And another example, which is known as the Gaussian kernel, or it's also known as the radius basis function kernel, or the RBF kernel. It basically says the inner product of X and Z is exponential of the minus X minus Z difference. So this is not a Gaussian distribution, but it's still quadratic in exponential decay, so we call it Gaussian kernel. It's not a Gaussian distribution, okay? It's not a distribution. So it just tells you what is the inner product of X and Z. It actually depends on the distance between X and Z, okay? And since it only depends on the distance of XZ, so it's a radius basis. If you have X here, then, everything here, as long as you have the same radius, then it has the same inner product, okay? And why it's called basis? Because such kernel can be transformed into a reproducing kernel Hilbert space, which actually use the distance with your training samples as the basis of that Hilbert space. Oh, by the way, a Hilbert space is a complete inner product space. So a real space is complete, a complex space is complete, but a rational space is not complete. So a Hilbert space is defined to be a complete inner product space. So it turns out that I lost the gamma hyperparameter here. So this gamma actually tells you how the inner product decays as Z and X are far away from each other. Okay, if gamma is large, then the inner product decays very quickly if Z and X are far away from each other. But if gamma is small, then it decays slowly. So it turns out to be this. I want to write things also in this transpose this, okay? For simplicity, let's think of X and Z are real numbers. That is simpler, I mean. I'm just giving an example, but I'm considering a simplified case, and I also assume gamma is 1. So this is actually exponential of minus X minus Z squared, which is essentially minus X squared exponential of minus Z squared exponential of 2XZ, right? And this is actually exponential. So I'm going to apply Taylor expansion for this term. And so Taylor expansion is fx is essentially the summation over n equals 0 to infinity if, nth derivative of x. Sorry. expanded at a, okay, x minus a to the power of n, and also divided by n factorial. So this only holds for analytic functions. If it's not an analytic function, then if x is far away from a by at least a small number, then there's no obligation what is the function value of x, okay? But if for analytic function, then this must hold, and exponential is an analytic function, and I can expand it at 2xz at 0, okay? I expand exponential function at 0, so it actually gives me summation over n equals 0 and to infinity and factorial, don't forget about that. I expand at 0, okay, but the exponential function at 0 has a derivative of 1, okay? Okay, has a derivative of itself, exponential of 0, and it's actually 1, okay? And no matter how many derivatives you take, this term is always 1. And this term is 2xz to the power of n, okay? Now we almost succeeded in writing the, the inner product into a group of x, transpose a group of z, right? So I can write exponential of minus x squared, exponential of minus z squared. I mean, this stuff applies to every term here, okay? So it applies into the every term in the summation. And then I can write, exponential of x2 squared, and then the square root 2 to the power of n, square root of n here, okay? But I only have one term, but I need to distribute to x and z, so I have a square root of that, and then I have x to the power of n, right? Then I can say this is 2, 0. So 2 to the power of 0, 0 factorial square root, x0 is 1. Okay, but I don't mind. Then I have the term of n equals 1. So this is 0, z. Okay, then I have n equals 2. Then I have n equals 3. So and so forth. Okay. This summation actually has infinite number of terms. Okay, so this is going to be an infinite dimensional vector. So if I specify my inner product or the kernel as the RBF kernel, it's actually mapping the features into an infinite dimensional feature. So I map from one dimensional scalar to an infinite dimensional feature, right? So the phi is mapping for this kernel, okay? It's mapping x to an infinite dimensional vector like this, okay? And definitely you see if SVM is doing linear classification in this dimensional space, it can be highly nonlinear in the original space of X, okay? And you see the SVM could be very powerful. And finally, I just want to mention one thing, but I just briefly talk about the result. This is the Mercies kernel. So not every function of, X and Z works, okay? It's not every such function can be a kernel. The kernel must be positive semi-definite functions, but when you evaluate at finite samples, it must be positive semi-definite matrices, okay? So the Mercies kernel is let's say x1 up to xm are samples, training samples, okay? Samples. Then let's define a matrix. Let's define a kernel matrix. Kij to be the kernel of xi, xj, okay? And the Mercies condition says Kij must be symmetric first. And it must also be positive semi-definite, okay? For any samples, for any finite samples, then by compactness, it tells you that the kernel function itself is positive semi-definite, okay? If you satisfy the Mercies condition, which are these, then exists some vector space that you can embed your data samples into that vector space, and then the kernel is an inner product in that vector space, okay? And this also tells you, for example, if you have two trees, of course, you can extract some features, but maybe your extracted features is very naive, okay? But if you can define a kernel based on trees, and if you satisfy these constraints, then it turns out that this is an inner product in some vector space, okay? And that vector space is not unique. For example, here I show a vector space like this, but essentially there is a principled way, which is the reproducing kernel Hilbert space, which is the span of the kernel of X, okay, where X is your data. So that's why it's called the basis. So your training samples now becomes the basis, and then you are defining a functional vector space, and your kernel is the inner product in that space, okay? So anyway, what you need to know is for valid kernel, it must be symmetric and positive semi-definite. And if you don't satisfy those constraints, it's not a valid kernel in principle, but sometimes it still works. In practice, we don't care about whether it's valid a kernel or not. We only care about whether it gives you good results or not. So, but to be more mathematically justified, it must be symmetric and positive semi-definite for any data samples. And the RBF kernel is the widely used kernel that maps your data into infinite dimensional space. You can think of that. And that's why it makes your SVM very powerful, okay? And it does the linear classification in that space, but of course it can be highly nonlinear in your original data space. But the question is your model generalizable, right? So if your hypothesis class is unrestricted, then you cannot generalize. I can just make some random functions to memorize your training data, and then I make an arbitrary prediction for test samples. It's not generalizable. But it turns out that SVM is also very generalizable because it's dual sparse, okay? Even if the primal features are infinite dimensional, the decision boundary is actually controlled by very few support vectors, and that's the trick of why it's generalizable. And there's many theoretical results telling you how generalizable are support vectors, okay? It's definitely related to how many samples that are support vectors, right? But that is beyond the scope of this course. Okay, I think that is pretty much for this course. And thank you very much for watching the video and hope you had fun in this course. Goodbye.